Hello, everyone. It's a great pleasure to have Cordelia Schmid here as our distinguished speaker on robotics and AI. So Cordelia is currently a research director at India with a joint position with Google Research. Since 1997, she has been in India, right? And since 2018 in Google, basically. She has done her PhD in Grenoble in 90. She defended in 1996, and she got the best thesis award. And basically, she has received multiple awards. Basically, I will not go through all of them, but most recently is Helmholtz Prize in 2023 for fundamental contributions in computer vision. And also she received ERC Advanced Grant in 2013, Humboldt Research Award in 2015, INRIA and French Academy of Science Grand Prize in 2016, Royal Society Milner Award in 2020, PAMI Distinguished Researcher Award in 2021, and finally Corber European Science Prize in 2023. She has been an associate editor, editor-in-chief, a program chair, and so on of multiple computer vision conferences and journals. She's currently a member of the German National Academy of Science, as well as she's also a fellow of IEEE and the ELIS Society. Thank you very much, Cordelia, for visiting us, and stage is yours.
Okay, thank you very much for the nice introduction. So today I'll talk about two recent works of mine. The first one is in multimodal video understanding, and then I'll show how we can use this video language models for vision language guided navigation and manipulation. So first of all, why do we want to do video understanding? There's a huge amount of video available and it's growing daily. For example, we have movie channels such as BBC or ENAT. We have YouTube, where there's uploaded loads of content, more than 500,000 hours of video every minute. And then we have more than 1 billion surveillance cameras worldwide. And what are the tasks? The first task is given short video clips, such as you can see here and here, that we want to determine which class these video clips belong to. And as we have seen here very nicely, we can hear very clearly in this lecture hall the audio, which is kind of very nice. We can actually see that classification should not only rely on one modality, but be multimodal, right? And so if you have the video of a clip of a birthday party, we can actually use the sound to determine and help you recognize what's going on. And similarly, this grooming an animal, you can hear that the water is put on the animal. And not only do we have audio, but we also have speech, which is even a more important cue if we want to understand multimodal video automatically. And we'll see in the second part of the talk that basically this can also be used then to guiding robotics. And then another task, maybe the long-term goal, is really to understand long videos. So you have a movie and you want to really generate automatically a script which determines what's going on. As the head waiter takes them to the table, they pass by the piano, the woman looks at Sam, and so forth. So we would be really able to describe not only short clips, but to really understand long video content. Okay, and so as I said before, why would you want to have this multimodal video representation? Here, for example, we can see an example where we can see that the man is serving food to the woman, but only if we hear the question, is this Indian, do we know that the man is, and the answer yes, that the man is serving Indian food to the woman. So it's really important to not just consider one modality, but to describe the content with multiple modalities. And the second advantage of using multiple modalities together is that we have actually a lot of potentially noisy training data online for which we don't need any manual annotation. So many of the instruction videos, which you can see here, come with speech, which describes what's happening in them. And if you use the speech ASR, so speech to text transcription, you can actually use this as a weak form of supervision and train your large language models on them, determine what are the similar steps, how things are constructed in the real world. So this is actually a huge amount of data which comes for free. And so I'll start off by presenting some of our very recent work on dense video captioning. So the task of dense video caption is exactly what we have seen In the beginning, what we have a long video with multiple events, and we want to determine the captions, so describing what's happening in the video, and localize these captions in the video. And so basically, you can see here an example. You have this long video, and you want to detect on the fly what is going on and to caption the video content so that you know what's happening in the video, and then also localize it temporally and potentially spatially in the video to see where it's actually happening. And so what are the state-of-the-art methods? In general, they train separate methods for localization and captioning. They require different task-specific event counters. They rely on manually annotated data sets, and they cannot reason over long videos. And so here, what our work does, it builds on recent localization as large language modeling approaches, for example, text-to-seq, which casts the object text section as a sequence generation. So you have here as an input the image, and you output the spatial coordinates, and the object outputs by language model. So basically, you have this input of image, and you output a sequence of tokens, which is the object category and the localization. And we'll see in a minute how we use this for our vid2sec approach, which does this dense captioning, video captioning. So here, what we want to do is we want that our model outputs a target sequence, which not only consists of the caption, but also the text, the time tokens. So we have a interleaved sequence, which are time tokens and text. So this output combines localization and captioning simultaneously, and we use one of these large language models to get this as an output. And then the second component of our approach, which is very important, is the large-scale pre-training. So as I mentioned previously, we have this automatically annotated data from automatically transcribed ASR, and we can use this for large-scale pre-training, right? So this is on the left, you can see the large-scale pre-training, and then the right, we have our approach for dense video captioning. And so in a bit more detail, what is our model? You can see we take as input the frames of the video. Each of the frames, they're sampled at 1 second a minute. Each of these frames is encoded with the frozen spatial encoder. These frames are then fed in a temporal encoder. We also, as I said before, it's important to use multimodal information. We also take the speech, so the speech transcribed with ASR, with the corresponding time tokens. So we have here the transcribed speech, which goes in with the time tokens. Time tokens are quantized, so we can actually see where in the video this speech happens. And then we feed this together in an encoder. So here we use the T5 encoder, and then the T5 decoder outputs our sequence of tokenized time tokens and the captions as an output sequence. So here you can see tokens, we have the full length, and we have a discrete step to tokenize the time, and then we can output basically these tokenized time tokens, which is the start and end time, and the corresponding captions. This is the model, and then obviously if you look at the model, it's large scale. And so here, what we use for pre-training is 15 million YouTube videos, narrated videos, where we actually have YouTube videos plus the speech transcribed by ASR. And the ASR, we use the ASR sentence boundaries to give us the event boundaries. Basically, this text, this short sentences gives us the boundaries, and we can use this for pre-training. Okay. For pre-training, we use two losses: the generative loss, where we have visual input and then predict the speech. But then we also want to have as input not only the visual input, but also the speech. And to avoid that we have the same input and output signal, we mask the speech. So this is called denoising loss, and then only predict these mask tokens. And then we can compare our approach to different state-of-the-art methods. So the first is a dense video captioning benchmarks. So Group2, VITT, ActivityNet captioning. We can see that our method outperforms state-of-the-art by quite a margin. You can also see that it works nicely for video paragraph captioning. So what video paragraph captioning is, you have a long video and you want to just describe the whole content by one sentence. And then we can also see that it actually works also if you just have a short clip on par with the state of the art. Our method wasn't designed for this, but it also performs well on this task. And so what's important, I don't go into details, but basically we have seen that pre-training is very important. The data size and the quality of the pre-training size matter. It's important to have the time tokens. They help when pre-training on untrimmed videos. Very important, visual and speech information is complementary. As I said before, if you have both types of information, you can get a much more precise description depending on the content. And then we've also seen that the losses are important, and in particular, the noising loss is important if we want to use the speech during pre-training. And then two qualitative results. So we can see here on the top, the input speech, then the input frames, and then in the third row, the ground truth, and in the fourth row, our prediction. And so what we can see is, for example, if we look at the first chunk, we can see that it's localized quite precisely in time. And then we can also see that basically the ground truth says cut the chicken, and our model predicts trim off the excessive fat of the chicken breast and cut it in halves. And so this shows one of the problems of video captioning, that obviously the captions are not identical, and so we need some more precise measures to compare them. But basically what you can see by looking at the results, that our model gives high quality results describing the video. So this is something which works actually quite well now. And the second example for sports videos, again, we can see time boundaries are not completely consistent with the ground truth, but we can see that our model describes the video very well. A woman runs with a javelin, she throws it on the field, and so forth. So it really understands what type of activities are going on in this video. And so basically, in conclusion, we have seen that we obtain excellent results for dense video captioning. Problematic are still the metrics and the variations of the details of annotation. So depending on what level of details we want, we need to have different levels of annotation. So this is kind of topics which people are currently working on. And then open issues are that small objects are not detected and described in the captions. There's problems with rare events like the long tail distribution, and we don't use any internal or external knowledge once we do this dense captioning. And for now, it's not done in a streaming fashion. So it's, again, something we're working on. And one thing we have recently done is to extend this not only to temporal clips, but to go one step further and localize and describe the objects in the video. So here what we do, we have a much more precise understanding of the content. We localize each object and caption the object in the video chunk. And so basically here the idea is that you really detect automatically video objects and provide captions for them, and this gives us a very fine-grained understanding of the video. Okay, and so let's move on to the second part. Again, it's visual understanding. So here the question is now, what can we do to improve the quality of these large language models? So probably, as you all know, in many cases, the answer is not completely predictable, and it doesn't allow to leverage outside knowledge. And so here, the idea is basically that we enrich our large language model with outside knowledge. So basically the first, here this is like a standard model. You have as an input a video or an image and a question. And then you have an encoder and a decoder, and you want to output the answer to the question. Okay? And so this is kind of limited because you cannot add any new knowledge. We cannot give access to any external data, and it's also, you have to retrain it on the fly every time something new comes in. And so here, this is recent work we have been doing to see how we can augment these models with multimodal external knowledge, right? So instead of just having everything in this black box model, we want to have access to external data, such as wiki image text, wiki data, or just also textual data, and use this data to enrich our models. And so why do you want to do this? As I said before, this allows us to do higher level reasoning and more fine-grained, more fine-grained in rare classes. We can disentangle knowledge from reasoning, and we can also think of how to do incremental learning without catastrophic forgetting, and make the models also more explainable. And so here, a concrete example where the question requires additional information, what part of this meal has most carbohydrates. And so basically, we first need to detect what is in the image and then get some external information, how much calories these different food staples have. And so what is our model? Our model has, as we've seen before, standard encoder-decoder based here again on T5, on the T5 architecture. Then we have this manual model where we encode each of our multimodal memory items, again with an encoder. And then we have a predictor which predicts for each memory item key. And what we then do during inference and also during training, we match the key with the query and can retrieve the closest items from the memory. We can then use these items in an attentive knowledge fusion mechanism where we weight them differently, feed them in addition to the image and the question, and then can use this as additional knowledge to predict our answer. And then for pre-training, again, obviously these models are large, we have to pre-train them. We use vision image caption models for the data sets for pre-training the model. And then if you look at the results, so this is one of the standard benchmarks, OKVQA. So this is a vision question answering data set where you need external knowledge. And what you can see here is that our model outperforms the state of the art. And in many cases, it's actually smaller. So this is the second claim we make, that by having this external memory, we can actually make our model smaller and get the same performance. And here, one example, which illustrates how it works. So the input image and the question on the top left, you can see what flag is on the umbrella. And then you can see the top two retrieved knowledge items. And you can see they both contain the flag. And you can see that it actually indicates that it's a flag of England, Union Jack of England. And so you can actually correctly predict the answer. And ideally, you can also look at these examples and see what has led to the answer. And similarly, the example for the bananas, again, you can see where in the world are these grown. First, you detect what bananas they are, what type of bananas they are, and then you can, from the external knowledge, you can predict that they're grown in the Philippines. Right, and then we can also ask, obviously, the question, how useful is the memory? So on the bottom, we have results without the memory, and at the top, with using the memory, and then we can remove the parts of the memory from our model during training and during inference. So in blue, you can actually see the curve, how it decreases when you remove it during training and inference. And then in orange, you can then put back the memory during inference, and you can see that this improves the performance. So this kind of says you can train it with little data and then add more data on the fly, and it still uses this data. And this is something which really works well. So this is something people are using more and more. If you want to have additional data or use something which is annotated and you don't have seen during training the model, you can really increase the capacity of your models significantly. And what is also nice is that you can make your models more explainable because you know which items are used during inference. And we can see that this gives excellent performance with large-scale models. Again, we need to have large-scale pre-training data. And as I said before, these retrieval augmented models implement and complement large-scale models. And so these models actually help us to improve the performance. And then one other thing we're currently looking at is, in addition to having this external memory, which we use during inference, we can not only use this in one go, but we can also use an LLM for reasoning. So instead of just predicting once which items we want to use, we can decide on the fly how to decompose the question, what information do we need to search for, so which objects do we need to detect, call an external object detector, and then the LLM can determine if the answer is correct or not, and see if we need to access to more information. Here there's also an API which searches external web pages. And so this is something which works very well, but as you probably know, this is very, very important that you do correct prompt tuning. So these methods, if you prompt tune correctly, they work very well, but for now they're still very brittle. If you go from one data set to the other, you still need to adapt the prompt tuning on the fly. But potentially it's very powerful because you can really integrate into your large language models different reasoning APIs and call these APIs externally and use them for reasoning. So this goes one step further from just using this retrieved memory once. This is currently work which we're looking at. Right, so this was my first part on multimodal video understanding and reasoning. And in the second part, I'll show how we can use this type of models for navigation and manipulation. Okay, probably you all know that what you want to do is you want to give a command to human command to a robot, go to the fridge, get the drink. And so what's important here is understand the language, see how the language actually corresponds to the visual observations in the world, be able to model the visual environment, and then plan and execute the tasks. And so I'll present a few recent works along these lines. The first one was the multimodal transformer for vision language navigation. And then we show how to integrate memory information into these models. And then in the last part, I'll show how we can use this for language-guided visual robotics. And so here, the task is, it's vision language navigation. These are synthetic environments that also show results on a real robot. But first, what do we have? We have an instruction: go to the bathroom with the orange stripes, make sure the faucet is not leaking. So these are data sets where you have environments, houses, instructions. You have training houses and testing houses. So the training houses and the testing houses are separate. You can have seen testing houses and unseen testing houses where it's more important, where it's more difficult, and you need to explore the environment on the fly. And so the first approach we designed was to have one of these fully transformer-based models. So what we do is what we have seen so far. In my previous work, you have the text, textual information, and the visual information. And here, what we do, we take this as an input and then have as output the predicted actions. And so here in more detail, what's important is actually to encode the history. So basically we have the text encoded by a language transformer. We have the history encoded by a hierarchical vision transformer. And then we have the current visual observation, again, encoded by the vision transformer. And then we have a cross-modal transformer, which predicts the action. So this is actually quite a simple model, but you'll see that it performs, at least in the synthetic environments, very well. And so here in more detail, we use a vision transformer for the single image encoding. Then at each viewpoint, we have a 360-degree viewpoint, so several views around the robot, and they are all encoded by this vision transformer. On top of this, we have the parameric transformer and then the temporal transformer. So we can basically, in this hierarchical encoding, store all the information of what we have seen previously and use this as a proxy to see what has been happening before. These models can be trained end-to-end with several losses. We use the common vision language proxy tasks, such as mask language modeling and region modeling. Then we predict the trajectory, but we also have new proxy tasks, such as symbol stack action regression and spatial relation prediction. Okay, and so we can see here on this different, so it's a bunch of different vision language navigation benchmarks, room to room, room for room, breviary, and so forth. We can see that in all cases, our approach outperformed the state of the art. And then if you look at the ablations in more detail, we can see that this is success rate normalized by the path length. The success rate is if the agent reaches the goal. Success rate normalized by the path length is how long it takes to reach the goal. We can see that our approach, the hierarchical temporal model, outperforms the recurrent model and the temporal only model, which doesn't take into account the spatial information. We can also see that using the vision transformer end-to-end trained approach improves over different standard vision models. And then here, an ablation for the different losses, we can see that having all these different losses together helps to improve the performance and stabilize the model. Okay, and so this model is quite simple, right? You'll say that it hasn't really learned anything about the environment, and we would like to have some more information, obviously, of what is going on. And if there's an error, how can we backtrack, right? So the next step is now, how can we add, and this is, I think, this is something which is still ongoing work, how can we add map information to these multimodal transformers and see how we can benefit from those? And the first one was the dual scale graph transformer, where instead of just having this fast forward local actions, what we want to add is we want to have a graph-based graph. It's a graph transformer where we have a graph, where we have this graphical map, which we build up on the fly. And this allows us to globally optimize our actions. Okay, so this is what we have here. We have the instructions, we have the encoding, and then we have a graph update where on the fly we see where we can navigate to as a next step, build up this graph, and then when we're at a given step, once we have this graph, we can then decide on the global level where to navigate next. And so if you look at the improvements, we get a significant improvement over by adding this graph model over just using this plain vanilla transformer model. As you can see here, the improvements are actually quite significant, at least on these two data sets. This was the winner on the VLN challenge hosted by the Human Robotics Interaction Workshop at ICCV 2021. Okay, and now basically you'll tell me, so still, these are still discrete environments, and what you want to do now is to move to more continuous environments, right? Actions are not happening on a discrete grid, but they're low-level actions. If you want to move to a real robot, we cannot use this. And so this is recent work where we have explored different types of representations. We can have an explicit representation, such as an occupancy or semantic map, but this requires accurate localization, which you might or might not have. Then we have implicit representations. We have seen that HAMD suffers from this inefficiency. It doesn't have any knowledge about the environment, no structure. And then the other method which I introduced requires accurate localization and a discrete environment, so it's also not applicable in the real world. And so the next thing which we introduced, and it's probably not the end of the story, but it's a step forward, is an implicit map to represent the environment. So have a lightweight encoding of the environment jointly together with these transformer models to see how to navigate. And so here, this is the goal. It's like goal-based navigation. So the goal will be find the sofa. We build up recursively the implicit map while navigating around the environment. It's a course map where we have a course layout. We see the course layout of the scene. It's quite small. It's a 5x5 map. So it just gives us an approximate information of where in the environment we are. And we can then use this together with a multimodal transformer to predict which is the next action we should take. And at the same time, while we explore the environment, the transformer updates the map with new observations. The map is updated on the fly. It's very lightweight, and it can capture the global layout of the scene. And it's initialized with zeros, obviously, for the new environment. The features from so we have RGB images are extracted with frozen clip. And then once we have extracted the features, what we do is we have at the same time, we have this information, the features at the current step, we have the multi-modal layer transformer and the implicit map which comes in. Then we have as output the updated implicit map plus the action which we need to take next. And this is done iteratively, so at every step we predict the next action and we update the map. So we can really, while we move around, update our map and see where the obstacles are and how we can best explore the environment. And then we have trained this on the Matterport 3D environment, which again is a synthetic environment which is annotated with trajectories. We have a number of auxiliary losses. So visual feature prediction to train our feature map, explicit map construction to see how this implicit map can be connected to the real world, and semantic prediction to see what the objects are, because in the end of the day, we're interested in what are the objects in the scene. And then if you look at how this model works, Here, the first one is just a recurrent state model. The second one is our hump model, and we can see that this recursive implicit map improves again over the previous model. And then interestingly, a small map size is enough. And basically, this seems to be saying that we don't need very precise information, but if you have a global information idea of how the layout of the scene needs to be navigated on, we can get best results here. And then we can also see that, as we've seen before, auxiliary losses are important. They help to improve the performance. And then again, so here, this is the state of the art on this Matterport 3D dataset, which is still artificial. And we can see that our approach outperforms the state of the art by a margin. And so here, these are examples in simulation. So this is successful cases. So the target on the top would be the cabinet, and then the bottom chest of drawers. We can see the image, and the next row is the depth map, and then the final is the navigation. You can see, actually, if I play it again, it navigates nicely through the house, and we can see this is Matterport 3D, which is actually houses which are reconstructed in 3D. So it's real houses, but it's still like artificial. It's not like real environments, right? But they have the real visual quality, and so they're actually very good for companies for pre-training our models. Okay, and then the next, so basically now, obviously the question where can we now use this to deploy it on a real world robot for object goal navigation. So here the idea would be tell the robot, go to the chair, go to the sofa, go to the plant, and then in a real environment which has been seen before or not, we can then navigate and find the objects correctly. And so here, the approach which we found works best is to first pre-train, also similarly what we have seen before for the visual models, to pre-train these models on synthetic data, or here the Matterport 3D, and then actually fine-tune it on a number of real-world demonstrations. And we found actually that this works much better than to do some sim to real, right? So basically, in general, if the sim to real is too difficult, it's very hard. So we found it much harder to do like data augmentation and things like this and do the sim to real. But if we fine tune on a number of real world demonstrations, which obviously we need to collect, we can get very good results. And so here we obtain, it's not perfect, you can obtain a success rate of 60% for 7 different objects, where the objects can be either not exactly the same instance on what it was trained. So scene would be if you have the same instance, and a different instance would be like, say, we have trained on other plants and can now transfer it to plants, right? And so basically here, why it actually is able to recognize the objects in a real environment is because we use these pre-trained vision language models and can extract this knowledge from these models. And I think this is something which we're also currently looking into as to how to further refine this, right? Because these models in general, they're just working on a frame level. And if you had a more precise object level, you could certainly further improve the results. Okay, and so now the results. So here, find the sofa. You can see that the robot is far away from the sofa and is now moving towards the sofa in the inner lab. You can see here on the left, the RGB and the depth information. Okay, and then a few more real world examples. So here, this is moving towards the plant. It's a scene, so it was an object category which was seen during training, but it's an unseen instance. And then the first example, it's moving towards the chair, and the chair has been seen before in a similar environment. So obviously then here, if the environment is very similar to what you've seen before, it's easier, but we have shown that you can also train it on one room and then move to another room and it still works. So results are not perfect, but they're kind of encouraging, and seems to be saying that if you have these transformer-based models, you can actually understand the commands, link them to the vision, and then execute them on a real robot. And I think to stabilize, the thing which we still need to work on more is how to make the combination between vision and language more precise, right? As I said before, now it's still like on a high level and not on a very low level for objects. We're also looking at how to make the models more aware of the 3D. For now, we're just having 2D models, and I'm thinking more and more having some more 3D information, such as point clouds. It always depends also on the sensors, is important. And then basically for the map building, think there's also further progress to be made on how to best construct the maps. Okay, and then the last part, we also, like we have now have been working on the mobile navigation platform, but we also want to do robotic manipulation. And again, doing this language guided with vision. And so what is the task here? Here, what we want to have is we have a number of instructions. And so here was actually nice, given that we have these very robust language models, we can have any type of instructions, right? You can say stack the yellow cup on top of the pink cup, or put the yellow cup on top of the pink one, or place the yellow cup on top of the pink one. And all these different variations are well captured by the language model. So we don't need to translate them into any reasoning or planner. It just takes this as input and can then basically determine what needs to be done. And then the similarities with the navigation. So basically it's language guided and vision based. So we have this backbone of language guided and vision based models. History is also important, obviously, but then what's different? What we found is for this manipulation, precise location is very important, right? If you don't have a precise location, you cannot grasp your objects correctly. So what we need is multiple cameras, and more we think that 3D information is necessary, but then 3D representation in the real world is obviously very noisy, right? So it's not completely trivial to get the correct 3D point cloud out. If you have it in simulation, it's very easy, but then in the real world, it's not completely obvious. Then occlusion reasoning and Brask prediction is important. Obviously, dynamic objects is something we're not really dealing with right now, but which needs to be also dealt with. And then robot arm motions are slightly more complicated. And here we don't need map information. And so here we have a similar model, which is adapted to this task, which is the Hive former. And so here the language is encoded with the clip model. So the clip model is visually grounded. We show that it actually outperforms the BERT model, which is not visually grounded. Makes sense. Then we have multiple view inputs. So we show that using more cameras improves obviously over having only one view. And we also show that encoding the previous steps over just having the current observation also improves the performance. We use a UNet. I don't know if you're familiar. UNet architecture is like a layered architecture, which is similar to what is used in diffusion models, just if people are familiar with this, and it's used in segmentation. And so what they do is they have a better spatial representation of the image layout. And this is actually important because if you want to navigate to one precise point in the image or point cloud, you need this representation. So here we have our image, we have the RGB images and the depth map, and then they're encoded by this UNet together with previous actions. And then we have the patch tokens for the different, as I said, for the different parts of the image, the channel tokens for the different RGB channels and the depth channel. And then we combine by cross attention what we have seen in the language and what we have seen previously with the current observation. And so basically the language tells us what we should do next, and the previous observations tell us what has happened before and what we have been doing before. And then we have as output the prediction of the position and how the robot should rotate, and if the gripper is open or closed. And so for the evaluation, we have used the Arrow bench. So this is one of the standard data sets where we have multi-view RGB images, 6 degrees of freedom arms, text description for each task. And the authors have provided 100 hand-designed tasks, of which we use 74. We can evaluate them in a single or multi-task setting. So single task setting would be we just train for one task separately. In multitask setting is that we can give different instructions and performs all the different tasks at once in one model. And so what they also have is they have an evaluation on unseen task variations. So then the textual descriptions becomes crucial, right? So you say, I want to first go to the yellow button, then the green button, then the gray button, or I want to pick up this object, then this object, then this object. So here we need the text. And then if we look at the performance, so auto lambda was the previous state of the art, we can see that here our approach outperforms significantly over the previous state of the art. There have been recently some other methods which perform on par even better than our method. This was at the time of publication. We can see that history matters. So for the groups, planning tools, and long-term, we can see that there's significant improvement by actually having the history. It makes sense, right? If you have a long-term action, you need to remember what you have been doing previously. And then, interestingly, also multi-view matters in particular for things where you have to be precise, such as screwing, screw driving, visual occlusions, and this type of tasks. And then here, an example where we have task variations. First of all, we go from seen to unseen. So unseen would be task variations. We can see that the performance drops, right? Because it's things which we haven't seen during training. And then we also did an experiment where we kind of changed the natural language to real language sentences. So for training, we just used the instructions which were given by the training set, and then we just created random instructions. And we can see again here the performance drops, but note that it hasn't been trained on this, but it still works. So this really shows that these models are robust to these variations and could be made even more robust by training on them. And then again, the question was, can we transfer this to the real robot? And so again, we had different tries. One was sim to real, which didn't work so well. And then it was like fine-tuning on a small number of real demonstrations. And we can see that here, without pre-training, on scene variations, it performs quite well still on the real robot, but then unseen variations, it doesn't perform well. But then if you do the pre-training, you can really see that the performance improves significantly. And so initial results we had here, push the yellow button, then press the white button, then push the blue button. And then here, unseen variations with different orders and real world instructions, which were created by humans. And then obviously the comment I always got, this is not realistic. So then we moved to picking fruits. And so here we can actually see, put a strawberry, then a lemon, then a strawberry in the box. And so here basically we can see that this performs well. So we can really give the instructions to put these different fruits. And it has just seen like during pre-training a few of these examples, right? So it was pre-trained on our bench and then fine-tuned a few examples here. And then the last thing we did is going from this multi-view to 3D point cloud-based representation. So here, instead of having multiple views, we just merge them in one point cloud. And so the advantage is that we have one better representation, which we can then capture from different viewpoints. And what we could also do if you have the point cloud, you could also inject more knowledge about the scene, which we're not doing here. And so here, what we do is we have these multiple cameras. We merge them together in a point cloud. This is possible because we have RGBD, right? And so we have these depth points which we merge together. We can clean them a bit, and we can also color them because we have the RGB data. So you can see here, actually, we can make these point clouds. We can add the features or the colors because we have the correspondence with the RGB images. And then we use here one of the standard 3D point cloud encoders, which is point next, which is quite powerful. And so this, we can then inject this in a similar transformer architecture. Here, what is interesting, actually, we don't use the history anymore. This 3D information seems to be, at least for simple tasks, sufficient. So this is interesting. And then if you compare to our high former architecture, we can see that it outperforms by a significant margin on our bench. And what's actually interesting, if you go to the real world, it performs kind of on par. It's much harder to get this 3D point cloud perform much better. And this is because there's like more noise, right? So this is kind of a bit sensitive to the noise, and we're currently it's now working, but it had to be some cleaning on the point clouds and some more vision processing, right? So it's not completely straightforward to get these things to work in the real world. And so a few ablations, we can see that by adding color to the 3D point cloud, we improve the performance. Makes sense. In this case, we don't only have the 3D structure, but also some RGB information on this point cloud. You can also see that using more cameras to create the point cloud helps. Makes sense also. And then some things which is important is removing the background actually improves the performance quite significantly. So this is on the real world also very important, right? If you remove the table, the noise on the table, and the noise on the background, you can even remove the robot. So by just removing all the parts where you know which is not part of what you want to act on, you can actually improve the performance, and this kind of stabilizes, I guess, your image visual processing, right? Because you don't have these noisy points. Particularly our surface is like blue table, which is metallic, so it has a lot of reflectance. So removing all this improves the performance. All right, and then the last part are the real world experiments. On the bottom, you can see the instruction. Take the green mark and put it on the middle part of the hanger. Let's see, it works well. So on 2 examples, pick up and set the yellow cup down in the pink cup. Okay, here, put food in the box, put the strawberry in the box. The baseball in the bottom part of the cabinet. This was kind of real task which were inspired by the Aero bench, right? Aero bench has all these different tasks and they wanted to make similarly complicated. Okay, they're not super complicated, but similarly complicated tasks on the real robot. Yeah, again, open drawer. Here, so the robot has actually to understand that it has to open the drawer first and then put the frog into the drawer. Here, you can see on the left, it first fails, but then kind of manages to perform the task again. So this can actually then, when it doesn't execute it, go back and redo it again. Then put the frog into the drawer. Place the white plate on the target. These are some failure cases. Okay, so here basically it didn't manage to get close enough to the hanger and then it fell down. And then basically, given now that it's in a failure state, it doesn't know how to recuperate, right? So basically, this is something which obviously is a case which it hasn't seen before. And so we would need to see how we can replan once it has fallen down. So that you basically add some additional data, how to once there's a mistake, you can then plan again and see that the cap has fallen down again and then put it back. This is something obviously which is quite interesting. Okay, so in conclusion, I think I'm out of time. Transformers can be used to predict actions. Standard vision languages models can be used to improve performance. We can use them. Pre-training data is very useful. It can be synthetic. I think this is very interesting. We found that the synthetic data can bring us a long way with fine-tuning. This is kind of in line what we have seen for the vision language models. We can use some external data on the web for pre-training, and then it's important to have some fine-tuning data to really adapt the model to the circumstances. And this is actually nice because it also holds here. So we have excellent results on benchmarks. Initial results on a real robot are promising. And then future research, there's a lot of still things to be done. We need better 3D representations. Very clearly, I think we need to kind of go back to all our knowledge from 3D vision and see what we can do there. Better memory and maps for the navigations is clearly also necessary. They have to be collected on the fly. So I don't think we need to have something where we want to produce these SLAM maps in advance and then navigate through them. We want to have something which is robust and can be produced on the fly. And then more fine-grained vision text correspondence. I think there's also work to be done, in particular, like if you have very small differences between the objects in the scene, this is not well captured right now. And then in the long term, what I'm interested in is to see if online interactions with the environment can further improve the models, right? And this is something where obviously our models need to still be more stable, but then once we have learned how to execute a command, we can ideally use this to further refine our models. Okay, thank you for your attention.